It's a low melt PAEK
the
resin.
LMPAEK.
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 Low melt PEEK LMPAEK resin from Victrex.
It is almost 100% your material.
We invented the PEEK polymer 40 years ago, and PEEK does many incredible things. It would be great if we could process it at a slightly lower temperature.
We've been able to reduce the melting point of LMPAEK, so we're opening the processing windows. The speed to manufacturing the parts, to lay up the tape is higher. It's out of autoclave.
You can do things in design that you would have never done in a regular composite, and you can do things you would never do in injection molding with different process, different materials. You can accomplish a lot.
LMPAEK was this innovation, but I'd like to hear a bit of the story behind it.
Yeah, so we invented the PEEK polymer 40 years ago. It's been in production and a part of many demanding applications for decades. And PEEK does many incredible things. One of the challenges of working with PEEK has been the processing, and what we heard pretty consistently from the market was we love the mechanical properties, the chemical resistance, the high operating temperatures that you can support, all of the things that PEEK does at the top of the polymer pyramid. It would be great if we could process it at a slightly lower temperature.
I go around and I look at different parts being made in aerospace, in thermoplastic, and it is almost 100% your material, which is very impressive.
It's pretty
when I say your
amazing.
material, I'm talking LMPAEK here.
Yeah, and I think part of that whole ecosystem that I was mentioning is that, yes, we make the polymer, but people need it in different formats. There's UD tapes, we'll make compounds, there's films, filaments, monofilament, multifilament, all sorts of different product format.
You, as a company, are very embedded with your customers.
Yeah, application development is pretty core to what I would say is our value proposition with the market. It's a very high performance polymer. We're trying to solve very specific problems. When you're trying to solve for application challenges, if there's another polymer that could do it, you do it with that polymer, right? But if there's that extra issue that you just can't quite solve, whether it's chemical resistance or damage tolerance, maybe it's even like the mechanical properties where you have those other things, but you just don't have the mechanical strength, then you start to look to PEEK and LMPAEK and that sort of area of the polymer pyramid to solve the problem. So we need to get pretty embedded in able to solve those problems. Our customers will always know more about their application.
Absolutely.
We understand our chemistry and what it's capable of and how to work with it.
Gilles, how are you doing?
I'm all right, thank you. Nice to meet you.
You were going to tell us a little bit more about the processes and the opportunities with LMPAEK material.
Right, I'm Gilles Larocque from Victrex and industry manager for aerospace and automotive transport. Here it's a good example of what we've been working on recently, like a rib for aerospace, like a thick part out of thermoplastic, all based in LMPAEK, which is a key material at Victrex. It's all about the value we bring in terms of automatic fiber placement, consolidation, the welding of a thick part, and by optimizing those manufacturing steps, we reduce the manufacturing time, reduce overall the cost of manufacturing the parts.
Got it. So let's talk about a couple of these processes then.
You
mentioned a bit earlier AFP. Now, what makes LMPAEK different in terms of for AFP you can actually reduce costs?
So it's a good question. So we've been able to reduce the melting point of LMPAEK, so we're opening the processing windows. So that gives more flexibility, more freedom to the customer to play with that window. And they can maybe, if we take that example, the speed to manufacturing the parts, to lay up the tape is higher. The quality of the bonding is better. So by adding them all those little things all together at the end makes a big difference.
So the speed of layup is faster because you have to put less energy into it.
A little bit less. And also due to the flow of the resin, due to the properties of the material, at the end of the day it's easier. In terms of defects you may have, with the steering properties, in terms of gaps between, let's say, two layers, you get rid of those little defects due to the resin.
And I've also seen that there's a lot of people who are using your materials, but what they're doing is they're not post-consolidating in a very expensive autoclave.
So you have different ways of making the part.
Yeah.
I think the one you're talking about is called in situ. So that means you don't have a post-processing steps. This is really somewhere the holy grail.
Absolutely.
We're not there yet, working a lot on it. But yeah, if you can skip, that's also a big advantage of overall thermoplastic.
Yeah.
But really LMPAEK to kind of skip these consolidation steps. We're not there yet. Today, kind of the way to go is a fast layup. Then you take the laminate, you put it in the autoclave.
Yeah.
Fast-ish consolidation. It's oven, sorry.
I was
oven,
gonna say that. Yeah, okay.
It's out of autoclave. That's
Okay.
at the oven.
So you can actually then put it into an oven, put it under vacuum. That's 1 bar pressure. That's not compared to an autoclave, which is very expensive. That opens a lot of freedom.
It's expensive, it's long. We can shorter the consolidation cycle.
Yeah.
It's a little bit less than, let's say, a PEEK or a PAEK material in general. So LMPAEK give all those benefits. The one I wanted to mention too, before I forgot, is the welding.
Yes.
So that's also a great, it's overall a feature for thermoplastic, but with LMPAEK too, we have seen that all the technology of welding like infrared, induction welding, also at the end of the day, the bonding meets the criteria. We are still working on it.
Yeah.
But in some cases, we can guarantee a good bonding between the two parts.
Dia were telling me that they welded the part, and I thought there was a material that was put in between, but actually they just welded the part straight away.
Exactly. You make the two parts.
Yeah.
So you make this part on one side, you make this one on the other one. You put them together. So in this case, I think it's infrared.
Yes.
But it's more or less always the same concept. You heat them up again, and then it's bonded.
Wow.
Due to the thermoplastic that can be remelt, back and forth. So that works pretty well. That's the beauty, I think, of LMPAEK that brings so much other aspect. Like on this one too, we've been working with this company, AVL and Minilab, to make hydrofoil.
Yes.
So nothing to do with aerospace, but a lot of similarities in terms of what's the problem to solve. For instance, here we've been replacing thermoset. So it's a great example of even the material. We all know it's more expensive than thermoset. When you take all the range of the processes, the layup, the consolidation, the assembly, I would say overall, of all those components.
So people tend to obsess about material costs, but actually you're looking at the whole process.
Yeah.
Most of the cost is in the manufacturing process.
Exactly. So it's really opening up new opportunities because initially, just because of the price barrier, people were not looking at it at all. Now we've been able to demonstrate, and that's why if you walk the floor here at JEC, you will see a lot of parts based on LMPAEK.
And it's just everywhere. Was that the MFFD program, Clean Sky too?
MFFD, we have a section here.
Yeah.
That's also what we've been working with these institute, DLR. So again, it's all about the layup of the skin, the co-consolidation of the stringer, the welding of that frame here.
Yeah.
So also combining back to what we discussed, the processes. It's a mix. You have to pick and choose the good process to make your part. So far, so good. We are quite just to see the adoption. We are moving into what we call the readiness level, the qualification process to show the safety, to show the reliability of the part. So still work in progress, but looking promising for sure.
Brilliant. Gilles, merci beaucoup.
Thank you.
Pete, how are you doing?
Great.
We were thinking, how do we tell the story of how do we go from metal to plastic?
Yeah.
And everyone is saying Pete is a man for it.
Well, they've lied to you, but I'll do my best. Well, we get a lot of parts that come in, and we sort of try to decide, is this mostly an injection molding part that needs some selective locations of composite reinforcement? Or is this mostly a shell that needs some areas of functionalization? So like this is a part here that we built that it's basically an injection molded part, except that there's some embedded composite stiffeners in here.
Yes.
So you can kind of see them. They all sort of blend together.
So which bits are the composite bits then?
You can kind of see it right in here.
Oh, right. So there's an inner ring in there.
Yeah, they're actually sort of like
of
two embedded question marks. If you were to just do the injection molding, it wouldn't be strong enough or stiff enough. And then the composite itself, you could never get all of these features.
So you got the strength properties and then the complexity that customers like.
Exactly. And you can do some like pretty simple shapes, right? Some pretty simple, this one's maybe a little complicated for show, but otherwise it's just a flat sheet and a flat sheet.
Yeah.
And you put those two flat things together and you can come up with a pretty interesting and much more useful bracket.
So the manufacturing on this is quite straightforward, I'll take it. Flat sheet that you get to CNC route or water jet,
Yeah.
place into the mold, overmold it.
Exactly.
Suddenly you have complexity and strength.
Exactly. This is another one where it's just two flat things, put it into a tool,
Yeah.
and you've got, take a couple of simple things, give it the strength and stiffness where you need it, and the function where you need that. The other side of the coin is when it's basically a flat or a shell
Yes.
with some shape to it that needs some details that you can't really get out of a regular composite. You know, you could never dream of doing this in a regular composite. I mean,
absolutely.
maybe you could, but it would be not very practical.
Very expensive. Yeah.
But you can take a nice composite lightweight shell and really sort of add features to it that make it something much more interesting. There's been a lot of really great demonstrators, but there's also a lot of really great parts flying.
Yes.
Ones that, you know, they come to us as a piece of hogged out metal that it's just so much wasted material. But if you could find a way to do it and put the right material in the right place, you get a much, much more efficient part in terms of material usage, and the process times measured in minutes, not hours.
In a way, when you compare that to a lot of metallics,
Yeah.
with metallics you got a big chunk of metal that gets machined down, and the value to fly is horrendous.
Yeah.
I've seen that multiple times.
Yeah.
In your case, you're almost doing additively, you're adding things together.
Yeah, pretty much. Yeah, this is a great example of that. The flat pattern for this, it's not much bigger than this. It gets stamp formed in the press and
Yes.
injection molded all in one step. It's got some
Yeah.
stiffening ribs here.
So you've got the stiffening ribs that get added onto the mold.
Yep.
So that's quite some nice complexity. And then you need these bond onto each other.
Exactly, yeah.
Right?
Yeah.
So complexity there, and then you folded it in this direction, this direction. You've done some complex jointing there too.
It comes from a hogged out piece of 7075 aluminum.
Was that Joby then who had a big metallic part, and then they wanted something a lot simpler?
They were part of the project. I can tell you that you know, it was a single piece of metal that spent a good amount of time in the machine.
Sure.
But this would allow you to weld it to the rest of the body.
So then you can have interfacing surfaces there that you can weld onto the rest of the wing, which
Exactly.
yeah, absolutely.
Yeah. Same thing here with some internal ribs on these faces. This is one of those parts where it's sort of half and half injection molding and composite. It's like a very enabling set of materials. You know, you can do things in design that you would have never done in a regular composite, and you can do things you would never do in injection molding. So if you can kind of see through the metallic design back to its original purpose,
Yeah.
and then build it back up with different process, different materials, you can accomplish a lot. But you have to kind of get beyond that metal machined piece and go back to its original purpose.
Absolutely.
We don't have many pieces up here that are welded, but you know, when you combine a stamp formed shell plus overmolding and then, you know, maybe weld something else on,
Yeah.
you can really get to some complex parts. And you know, maybe throw some metallic inserts into the injection molding. Really, the only limitation is sort of the creativity of the designer at that point.
Well, thank you very much for your time, Pete. It's an absolute pleasure to speak to the people who are kind of like at the tip of the spear.
It can be a lonely place, the tip of the spear.
Yeah,
you know, when
yeah.
you're trying to explain this to a tool maker.
Absolutely, I can imagine. Yeah.
So.
Perfect. Well, thank you very much.
Thank you. Yeah. Nice to meet you.